most people here. We'll get started. Please try to finish homework 1 peer reviews by Friday, please, so that we can get started grading it. We want to get homework 1 graded faster than homework 0, and that will help us a lot. Homework 2 is out, in case you missed that, due November 2nd. Please check if Python works for you in homework 2, nowish, right? If you get towards the last weeks and you're having trouble, it's not going to be pleasant for you. For Friday's lecture, we'll have a guest from research computing who will walk us through using Odyssey, submitting jobs, understanding good behavior on the shared compute resources at Harvard. Please try to log in. You should have, if you haven't already gone through logging into Odyssey before, haven't learned how to submit jobs, things like this, please try to do that. Please make sure you're here Friday. Log into Odyssey, just get through the 2-factor authentication and parts like that before Friday. And then Friday, he'll go through, basically, bring your computer, be ready to run through things there. There'll be an example there that we'll supply that will basically use OpenCL, which is the GPU programming language we're going to use. Just a quick example to make sure that you're set up to submit jobs to the GPU cluster, or subcluster. All right, today, review session. Not many questions on Piazza. I'll answer the ones that were there and discuss them more, and then please ask questions, anything that you want to talk about. There was a question about partial iteration in AVX. All right, we've got 8 floats in a single register, or a single value. How do we iterate over parts of them and do some computation, but not all of them, right? How do we do something to just some of the registers based on some condition? We use the same trick, although not automatically as they did for GPU branches. If we have this code that we want to run on 8-way parallel SIMD instructions, we want to check if x is greater than 0 and do one thing and otherwise do something else. We basically do the comparison and then set some, in the GPU it's automatic if you can run this code. It masks off some of the computation. It says, okay, it's true in these 3 cases, so run the computation there and just idle for the others. And then switch the mask for the else clause and do the second half of the computation in this block, and then continue on in 8-way parallel land. That's automatic on the GPU. For AVX, you have to do it yourself. Okay, so comparisons are test operators, and all the sort of branching-based things you might want yield either all 1s in the sub-register, right? You have 8 values. So it puts all 1s, which is equal to minus nan, or all 0s, which is equal to 0. And the way to use these to do branching is we use AVX AND to mask certain values in the computation. I'll show the example that we did there. So that's the code for GPU land. Check if every value is greater than 0, do one thing, otherwise do something else. You can do it in AVX this way, okay? So check the mask, x greater than 0. So this will actually be an AVX compare function call. And 0 will have to be an AVX register full of 0s. Set that as a mask, and also compute its inverse. And then you see this temp, you have 2 statements, right? You either take, so the temp equals x to the power of 5. Sorry, I swapped it here. It should be 5 instead of 0.5. So and the mask with x. That's bitwise and. So when you do that, every value of x that corresponds with all f's, which is true, will be kept as x, because it's bitwise and. So it's all 1s. It's whatever is in the x register. Anywhere where the mask is false, it contains all 0s. When you AND it, it wipes out that value. And then we just recombine, so we compute some of them. We compute to the power of 0.5 after masking them off. And then we invert it for this other one. Right? We AND those together. And then we recombine them. We could use OR, but since it's 0 where it's false, we'll just use plus. It should be to the 5th power. Yeah, that's just my error. And then we can go on with 8-way parallelism for the last line. that clear? One problem, we didn't give you AVX not. I don't think you actually need it for this problem. It's not that hard to add a wrapper. There are 3 files, the .h, the .pxd, actually 2 files, .h and .pxd, that have to be modified to add a not. If you really want this, I don't want to put it into the GitHub base for the homework, because I just don't want you guys to have to do pull requests partway through the homework. Or not pull requests, git pull partway through the homework. But if you really want it, we can add it there, or you can ask on Piazza how to add it. If you feel like you need not to translate problem 4.
So here, x is an AVX value?
So here, x is what?
X is an AVX value?
Yes. So this is, assume everything here is an AVX value, everything. Including 0.5, sorry, 5.0. All of these would including 1. When you're dealing with AVX, you can only really combine them with other AVX values. So this would be actually an AVX, so from float, I think is the name we gave it. It's got some M256 intrinsic name. The comparison is actually done as a function call.
Yeah, so that grid is like x greater than 0. You can't just do that, right?
You can't just do that. You have to set up a 0. There might be a comparison to 0. Actually, no, I don't think there is. You have to set up a 0 using from float. A 0 AVX value, your x value, call, we gave you AVX greater than. There's actually it's a comparison operation that takes a comparator there's a huge number. There are something close to 128 possible comparison operators based on all kinds of different choices. The AND is a function call. The power is going to be a function call, which we also didn't give you, but you don't need. Hmm?
So very, very basic question. So the mask then is sort of an AVX object of 8 true-false values?
So the mask, is it an AVX function, or sorry, AVX value of true-false values? Yes. It's zeros bitwise everywhere for so AVX register in the cases we're talking about are 8 floats, right? You can split it differently, but 8 floats in our case. When you do a comparison, anywhere that comparison is true between the 2 float values, it'll be all 1s, bitwise. Floats have a complicated relationship between bits and what the actual value is. In this case, it's minus nan. The minus sign is important, right? Because we can pull the sign off very efficiently into an integer. So if we had, let's do it with 4 for now. 1, 2, 3, 4. These are all floats. And we want to compare it to 2. And we say greater, we'll get a mask value out. And that will look like 2 ways to look at it. I'm going to draw it first in floating point form. So greater than, not here, so that's 0. Also not greater than. Greater than here is minus. Greater here is. Okay. These are a pain to deal with. So that, usually the way you would deal with them is not as floating point values, but as their bitwise values, in which this is all zeros. Oops. This is all 1s. And then what you can do is, if you go back and, for example, and these together, 0 and anything is going to be 0. So it's just going to be all zeros, which is 0. 1 and anything is that thing. So it keeps this value. So if we and these together, we get And then we add them. Exactly. I mean, it might have made more sense to use or there, but when you're talking about adding 0 or oring 0, same thing, right? Or of 0 with anything is that thing, plus 0 with anything is that thing. And by the time we get to that step, it's all either 0 or a value. We've gotten rid of these through the AND operations, through the masking. Okay?
So you can effectively understand that it's going to go down to the bitwise representation, but it's just boxes of floats, and it's going to be boxes of zeros, or falses and truths,
Yep.
that are really represented by 8 zeros.
Yeah. I mean, 32. But, yeah. But yes, and you'll almost always use those. They're represented as a box of 1s or 0s, and you'll use those with the AND operator to select off certain operations. If you find yourself in the code and say, I wish I had or, I gave you greater and less than, I didn't give you greater than equal to, if I don't have a not, things like this. If you hit this point in your programming on problem 2, 4, 3, which one's AVX? Whichever problem it is, 3. If you find yourself saying, oh, I wish I had not, I wish I had or, I wish I had some operation that I know is actually there, post on Piazza, catch us on Slack, something like that, we will give you the code to add that operator. That's fine. I gave you a basic set. There's much more there. If you need it, you can ask.
So this box of numbers, you don't call this a list, you don't call this an object, it's a register.
It's called a register because it maps to physical registers, and you're at a pretty low level. It's an 8-way float register, and your operations are, and you're close to assembly programming here. Sad but true, but it's how you get access to these if you want to guarantee that you're using them. The compiler, if you're running some sort of operation that's across a bunch of values, you're going through an array, computing something for each element, the compiler can, if it's not too complex, discover the parallelism there and use these automatically in a lot of cases. But as your loops get more complex, or if you're calling functions on different parts of it, then it loses that ability to do it automatically, and you fall back to single register computation. So to guarantee access to it, you almost always have to, well, to guarantee it, you have to go in and do it by hand. Many of the computations you do in image processing, data processing, you know that you have independent values or limited communication between values, and you can figure out how to map it to this reasonably easy. And you often have tight computational loops where the operations are just multiplies, adds, and simple operations like that you can quickly translate into this once you step up just a small amount to get to that 8-way or n-way parallelism. More questions about AVX? We gave you the toMem function in there. So there are various ways in the AVX instruction set itself. We exposed one of them, AVX.toMem, which takes a register and a float pointer. That float pointer should be an array of 8 floats. If you need I think there's an example at the bottom of the PYX file in the homework. It's down at the, oh, then just get pull. Yeah, so if you don't have the toMem function, then there was half a day when I didn't have that function in there, and I added it and posted. If you get pull in your repository from upstream, you should get that. If not, go to the GitHub page, and it's at the bottom of the PXD file and the .h file. And there's an example at the bottom of the PYX file that uses it, that shows how to pull out examples, or how to pull out values and then deal with them. When you're trying to convert to integers, which you'll need to for the Mandelbrot set, because it's a map of complex to integers, you'll have to pull out the floating point, convert it to an integer, and write it to the output array. Okay. More AVX questions? There's a question about parallel versus p-range on Piazza. Parallel says however many threads. If you don't give it a number of threads, it defaults to the number of cores, I think. So just do something in parallel across these threads. So this first block is a parallel block. It'll execute that statement for every thread separately. It'll execute it exactly n times, where you have n threads. So if you say num threads equals n times this will be executed, but basically a parallel is split out into n threads and continue in parallel down this next bit of code. Because of how parallel works with variable assignments, that'll become thread private. So that val will be unique. It's not a shared variable. It's unique to each thread that is now running. Okay. P-range, this statement will be executed n times, right? Because L times for number of loops, because it's a loop. It's just it'll be split somehow amongst n threads. Right? We said n in we don't know which thread will do which iteration, but every iteration will run once. You can nest a p-range inside a parallel. Actually, is that my next slide? Oh, first, is that difference clear? I think my next slide does actually use this. So the most common way to use this is use a parallel block to set up a bunch of thread private storage, and then do a p-range where you loop over that storage to do something. So this is a trimmed down example from just the Python homepage. We start with a parallel block over some number of threads, and we allocate a buffer of whatever size we need, and then we initialize it right here. So before this p-range, everything is basically thread parallel, and we'll do it once per thread. So each thread then loops over this, does that loop. That's a serial loop per thread, that for loop. Okay, it initializes the local buffer. Buffer is thread private. Each thread has its own buffer. So it initializes the local buffer. And then we loop over some different value, n, but we don't necessarily say what it is. And we call some function with a buffer and maybe other arguments here. The buffer is a scratch space or some temporary accumulation or something like this. And this loop will happen, again, it'll be a work sharing loop, exactly as if the p-range had appeared outside of the parallel block, but it'll just use the threads that you already created. In fact, you can't set a different number of threads here than what's on the outside. So that's the most common use of parallel versus p-range. Parallel is almost always just a wrapper to do some setup per thread before doing a work sharing loop.
Can you explain what you mean by using the threads you already created? Because parallel is going to do this n times for n threads, but then p-range should do that
So
two n times
yep.
split between the original and threads. Yep. But there's one p-range for each original thread.
I didn't set the number of threads in parallel there. So parallel will create when you encounter a parallel statement, it'll create some number of threads. You can control that. By default, it'll be the number of cores. So by default, this might be 4 or 8, okay? So there are 4 threads, and then the block before the p-range will happen in each thread separately. It's basically a local computation within the thread, okay, and it sets up its buffer. And then this n could be 1,000 or anything, right? This function is going to be called that number of times. It's going to be called within the thread. So now I have basically I have 4 workers that started with the parallel and now exist here. So it will take this n and somehow split it up amongst the 4 workers. You can't create a new set of workers here in Python.
It's just smart enough to split it up, right?
Yeah. So it'll choose some scheduler. Probably, I think the default is static. So it's going to give it. Exactly. That p-range, so above that, everything's working in, working in parallel across the blocks, 1 block per thread executing. When it hits here, there's a barrier. It basically says, okay, wait for everyone to be finished, and then launch this p-range using the workers that already exist, using the threads that already exist. Okay, clear? Okay, good. Exactly. It was just for setup. It was just, I need to do something. I need to do some amount of work per thread, and then I need to do some amount of work over some n. I need to do some early setup. So that's the reason to do it. You can use it other ways, right? You can use, so in the higher level Python, right, we had these, some of the examples before and that you'll need to use for the image processing problem. We create a bunch of threads and send them off to do work, right? We set thread.daemon true, and then we call thread.start. And then these threads start up and go do something and wait for work to appear and such and such and such. You can do that same trick with parallel, right? You don't need a p-range in here. You could call some function where it goes and does something, and I just launch a fixed number of threads with the parallel, and I send them off to do work that basically I'm in a schedule. I'm not gonna do some sort of loop. I'm gonna say, okay, I've got 4 threads, go do this work. When it's done, come back, and it'll just automatically join together when all the threads are done.
What is the buffer that's
Scratch space or something like this. A lot of, various functions may require. So it's much more common, for example, in Fortran, right, where you're doing a matrix multiply, and it says, okay, if you're going to multiply a matrix of size n by n with another one of size n by n, I need 2n scratch space. Pass it to me in an argument so that I know that it exists. It's not, it's unclear, just generally, you might need some sort of pre-computation that's per thread. And then after that, you're going to do a computation that just needs that scratch space or needs some sort of information that needs to be set up for the thread before it starts doing work sharing loops like this, p-range. Sorry, go ahead.
In your p-range function here, in the previous slide, you had an L for the number of times it runs, and then another value for the number of threads within a run. So here, I'm assuming n is the L.
Yeah. Yeah.
If I were to then say a number of threads in p-range, does that be a subset of what the parallel is?
You can't actually do it. It won't even let you. I think you might be able to in raw OpenMP. And in fact, in the newest version of OpenMP, I think you can even have one thread start up a bunch more threads and then they join back. But in Python and the earlier versions of OpenMP, it uses however many threads you created there is the number of threads you get there.
This is sort of the right practice. You sort of set the number of threads in parallel, and then if you want to utilize them.
I mean, if you don't have any setup, you can just call p-range directly.
Okay.
Right.
And you would specify the number.
And then you would specify the number of threads, or just let it choose. I mean, it'll choose the number of cores you have, which should be good.
Why wouldn't you just use a normal range in that instead of relying on p-range?
Well,
You're already parallelized it. Parallel, right?
so if I use a normal range here, so remember, when I come into a parallel section, I basically fork off however many copies, and they continue down through here. So that, for example, that range, if I have 4 threads, it loops from, each one goes 1 to size. So it's number of threads times number of size. If I turn this into a range, now I call function how many times? If I've got 4 threads, how many times do I call function here? N times 4. If I do it with a p-range, I call it n. Right, this is a work sharing loop. So the fact that it's in the parallel, this is no longer run in that parallel stream the same way. It stops here. It says, okay, I've got a work sharing loop over n objects. Schedule those n objects to the existing threads, in this case 4 that we were talking about. So schedule the existing n objects across 4 threads and have them do their different indices in separate things and then join back here. And then I could have more, well I do. This is run back in that 1 per thread land. Okay. Yeah, these do just set pragma marks. In fact, so if you just run Python, I encourage you to do this. Run Python on a PYX file. It will spit out a .c file. The pix import structure that we've given you hides all of this in under OSX, it's .pix build in your home directory. It puts all the C files and all the modules there. But if you just run Python, you'll get a C file. And you can open up that C file, and it's huge, because it's computer generated. And it has a huge amount of prelude. But if then you search for your Python code in that buffer, or in that file, it puts each Python line and puts a little mark. This is the Python line or Python line I am translating right now. Here is the C code I generated. Sometimes that's very short, especially in no-GIL sections. Sometimes it's very long. And when you have p-range or parallel, or it'll have these, it'll just have the pragmas. You can just search for the pragmas. You can see exactly what it's doing. We were doing that, Adi and I were doing that earlier when trying to figure out why some loops were slowing down a great deal, particularly in the threading case, or in the locking case, looking at the actual C code and trying to figure out what was going on. So you can do that and see what's in there. It's kind of interesting. But it's also useful because then you can see, okay, I think I'm doing C. I think my code should be very efficient. You go in there and you see, there's a lot more Python code, or a lot more code in here than I expected. I'm doing something wrong. I don't have a type declared. I don't have something else that could be, there's some hint that's missing to the Python compiler.
So it seems like there's a lot of other ways you could do this. Like why, like for example, you get like a parallelized queue or of just like the M members, or maybe even just pass into the threads themselves, like split up and pass into the threads themselves. Like why is this the best way to achieve this?
It's not necessarily the best way. There are a lot of ways to get at parallelism. This is not, I'm not going to say this is the best way. It's an easy way, and it's often as efficient as anything else you could do. You do this, use the low-level parallel constructs when you know that your problem can be solved at that level and can be done efficiently, and you don't want to pay the overhead of using something higher level. It's very useful in low-level code. So, like,
To me, it's like a really weird construct that I think that this key range thing. Like it seems really useful. It's just very odd
coming from where?
like from other languages.
Coming from other languages. It is a somewhat of an odd construction. There are analogs. I mean, certainly OpenMP, it's basically a translation of the OpenMP structure, which a lot of people use in C or Fortran, just to Python, pull in the minimal amount to do it. So if you've coming to this from OpenMP land, which I didn't, I think is much easier. If you're doing something that's low level, if you're dealing with matrices, images, something where you're doing a computationally dense, or you're doing just something that's not low complexity at the bottom level, it's very efficient. It's very easy, right? If I was just doing, iterate or increment all these values or add these together, then I get threads, they go off and run, and my code is very short. So it's much more about simplicity of access to the parallel structures. I could do it in Python threads. I could do some similar tricks, but the code gets longer, right? I have to set up a worker, I have to set up a queue, I have to do this. And I pay an overhead there as well. It's both in terms of how much, how much I have to type, how much code I have to manage, whereas this is very short, if my problem is simple enough to map into this space, which it isn't always. There's sort of there's a trade-off, right? I could go down into libp threads and do all kinds of crazy things, but this would be more low level, and I might do that if I want it to be very, very fast with very little overhead. But I don't know if that answers your question. There are trade-offs in here. You'll see. I mean, you'll see some of this in the image processing where I ask you to use like semaphores or something higher level than just locks. You'll see that some things are easier to do this parallel computation. Some things are going to be more typing and more management of what's going on than what I have here. So for simple cases, this is fine. I do something simple. More about parallel p-range. Differences, so what are the differences in the scheduler, static, dynamic, things like this? In what you're doing here, just use stat. I think all the problems we just asked you use static, which I think is the default. In general, you can just let it be the default. If your work is all the same, roughly, because you want to be balanced, right? You want all your threads to work until they're all done, and then they should all end at the same time. Static is good. Minimal overhead, right? Take this, break it up this much. Everyone gets their pre-allocated work and goes. Dynamic and guided are both when you have a highly varying work size. Guided, I think is hard to figure out what to do. There's also runtime, which checks an environment variable, so you can switch between these. So if you really want to experiment, you can do that. Dynamic is good when you've got variable amounts of work, and you don't know what it is beforehand. It'll send out, and you set the chunk size small. You send out work, and then it gives them to the, it's dynamic, so whoever comes back and asks for more work gets more work. You've got overhead then because you've got more communication. Guided does something in between, or like sort of starts out dynamic and then eventually switches to a static case. Static's almost always fine. Certainly for everything in the homework area, static should be fine. So it's more if you have variable workloads. Okay, more about this? No. This is the sad slide, debugging. How do you debug Python and threads? There's no good answer to debugging threads usually. And it's easier in Python because you can switch between them and figure out what's going on. If you're hitting a bug, run with one thread. Is it still there? If it's not still there, it's probably a data race or something where you're not protecting a shared resource. And when you run with one, then you don't run into this problem. And just add prints. I'm grabbing this lock. I'm letting go of this lock. You can put those in the lock functions themselves, the acquire and release. You can dig into your code. We're down, to get the performance, we're gonna go drop down into C-level code. Looks like Python, but at the bottom it's C. You can use GDB or LLDB if you've used them before. This is useful when buffer overruns, things like this, where you have memory access problems or other crashes that you're not sure about. If you haven't used them before, it's not gonna be an easy path. And I think we've tried to structure the homework so that you don't actually need to know C-level coding as much as possible, that you can think about it on a higher level. If you do start hitting crashes, then we can maybe help you with this, but it's not the path you want to go. There is a Sci GDB built into Python. It needs GDB2 installed, doesn't work with LLDB. It's a real pain on OS X to actually get going. I managed to do it after about an hour yesterday. It gives you access to Python variables, and you can ask questions about things like that, but it's unfortunately difficult. Print is really your best friend in this case. Threaded programming is hard. You want to reduce it down. You can, if you've got some idea for an algorithm for solving something with threads, write it in Python first. Make sure it works there. Figure out what your scheduling is, or your scheduling problems, or work division, things like this in Python. Make it work there, and then once that works, translating it into lower level Python is easier. We'll help you as much as possible. We may tell you this is not the right direction to go. You really want to back up and do something different. But just instrumenting your program with information about what it's doing can often give you an idea of what's going wrong. Deadlock. There's some questions about deadlock. So classic case is two threads, A and B. One of them locks lock 1 and lock 2 in that order. The other one tries to lock L2 and L1 in that order. A gets L1, B gets L2, and both of them stop waiting for the next lock and cannot escape. To avoid deadlock, just always lock in the same order. Doesn't matter which order, just choose an order. Okay. This one will matter on problem 1, may matter on some of the later problems. It wasn't. It deadlocked. I switched the code, and I thought I pushed the version that still did deadlock. I swapped the two locks to make it work. So the difference between the working and non-working code is just the order of locking. But I may have pushed, my example may have ended up with the working code, but if you switch it back to something that looks like this, it becomes more, it just stops. Double locks are related. You can't do this in one thread. You can't acquire a lock and then reacquire that lock. You already have the lock. You're a thread trying to lock a already acquired lock. You hang. There are reentrant locks in Python threading. They're called R locks. Well, you can do that. You just have to release, if you acquire it 3 times, release it 3 times before it's actually unlocked. OpenMP has reentrant locks. They're called nested locks. We didn't give you code for these in homework 2. in problem 2. If you really want to go that route to simplify your code, you can add it pretty easily. It's basically a cut and paste from the lock supporting code to nested locks and changing some function names. It would result in slightly smaller code, but I wanted you to think about deadlock and double locking more than about whether or not to use these tools. So it's your choice which path you take. It's just a form of deadlock. There are some structures that go around it. I think we already answered this one in the AVX talk. How to get integers out of floats in AVX. Write it out, get a buffer. You can even hand code it float blah 8. That gives you an array of 8, just like in C. Use to_mem, and then you just loop over those integers to extract them. You might need to use this cast operator to actually turn them into ints, but I don't even think you need to do that. But you can, right? So that's how to extract things from AVX. Oh, I'm done. Anything that I went over that I need to go over a little bit more, or other questions that weren't posted? Classes in Python that don't need the GIL. You mean, so that basically turns into a C class. You do them with CDEFs. You can build classes that way. It's not within the scope of this class. So if you want to talk about that, I mean, the documentation is pretty good. There are examples out there. You can create C++. You can create C-level Python classes. You can wrap C++ classes in Python code pretty easily. Other questions? Everything is clear? Yeah, that one's a pretty easy threading problem. The threading part is not hard there. Oh yeah. Well, not in threading in Python. That one is a p-range problem. So that one should be threading in Python using p-range. And that does give performance increase. We've seen in the earlier examples using Mandelbrot as just a compute thing to do, that you can split it up across Python threads and get good performance increase. We did it on subprocesses and in threads. And we saw roughly the same, because it's a Linux-like system. We saw, yeah, you can go back. In this one, we asked you to do it for p-range to loop over. The real improvement there will come from the AVX, right? You can get 4 times faster on 4 cores, but you can get 8 times faster on a single core with the AVX, and can get close to, I don't know what sort of peak we were seeing on our example solution, but it was pretty good. We were getting above 50% of the maximum possible throughput on the machine. So, which is surprisingly high compared to, I mean, it was already pretty fast, but you can get, the AVX stuff is really very performant.
The syntax question, what does it mean? You mentioned it earlier when you have like those kind of greater than, less than signs on either end of stuff.
Oh, yeah.
Whether we need that or not, I'm not sure, but you use it other times.
So this is basically, this is a cast operator. In C, it's parentheses. But that means something in Python. So they use this greater than, less than. And that means interpret everything to the right of this, its memory representation, as if it were this other type. Not its memory representation, sorry. Convert this type over here. That was wrong. Convert whatever is over here into this other type. So for example, if I'm calling a function that only takes an integer and I try to pass a float, that will probably work, but if it took, what's a good example? It wants a character pointer, it wants a string, and I've got a pointer to an integer. I can convert pointers, and that's where you usually do it. So like we have a bunch of malloc calls in there that have something like this. Malloc returns a character pointer. So it has a type, and it's a pointer to an address, which its claim should be interpreted as characters. But we want to use it as an integer or a float or something like this, so we convert the pointer type using this. You probably don't have to add any code for this. This is probably not actually necessary because numeric types convert automatically. If I assign an integer to a float, It just turns into whatever, converts it to a float and then assigns it. So I don't think you'll need this in particular. It's more when you start dealing with buffers of different types, or sort of like as type in NumPy. Other questions? Okay, let me go back. So again, please log into Odyssey before lecture on Friday. Talk to us if there are problems. Talk to RC if there are problems. I posted on Piazza the 2 links that you can use to get help. I also posted on Piazza the link to the instructions for getting set up, which I think you should have received in the setup email. Also, if you haven't already tried to run all the examples, all the homework problems should run as is in what you check out, and then you just have to make them threaded. Not necessarily faster, that's something to be aware of. This homework, you may do something, may not be faster. That's fine. Don't expect it always to be faster. But do make sure they work. Let us know soon. All right. Is it Friday? No, it's Wednesday. Okay, then don't have a good weekend yet.